Hi students, welcome to my lectures on chemical engineering thermodynamics. I request you to follow my lectures from the beginning as every lecture is connected. In the last two classes, we have discussed about how to find out the enthalpy and entropy in a mixture. It could be gas mixture. Okay, in today's lecture, we come to the main agenda to find out the partial molar Gibbs energy. Using the informations of partial molar enthalpy and partial molar entropy, now we have to find out the partial molar Gibbs energy and what is its importance. In any reactions or separations or mixing, chemical potential is the driving force for anything to happen. The partial molar Gibbs energy is nothing but chemical potential. That is why we were discussing about the partial molar properties to reach to the conclusion today, which is called partial molar Gibbs energy, and in other words it is called chemical potential, okay, which is the driving force for any reaction, separation, mixing to happen. Okay, let us discuss about this partial molar Gibbs energy, in other words chemical potential. And you know, because we are going to use the last two lectures formulas, okay, we have already evaluated what is partial molar enthalpy, we have already evaluated what is partial molar entropy. So let us evaluate. There is a mixture, our agenda is to find out what is the partial molar Gibbs energy of A in this mixture, what is the partial molar energy of molar Gibbs energy of the B in the mixture, okay. And any partial molar property, you can see partial molar Gibbs energy of ith component at specific temperature and pressure is equal to the partial molar enthalpy minus T into partial molar entropy. That means you know G is equal to H minus Ts. H is the enthalpy, T is the temperature, S is the entropy. That means if you know the entropy and enthalpy, you can evaluate the Gibbs energy. So partial molar Gibbs energy is nothing but partial molar enthalpy minus T into partial molar entropy. And this is what the last two classes we have discussed about what is the partial molar enthalpy of this mixture is nothing but the pure value of this enthalpy of A, any specific I component. Similarly, partial molar entropy at specific conditions at temperature and pressure, which is nothing but enthalpy of pure, partial molar entropy at T and P is nothing but the pure entropy at temperature and pressure minus R ln YA. Is R ln YA comes from the mixing of A and B, because entropy will come with the mixing, okay, randomness generation. So let us substitute these two into this above formula. Finally you can evaluate what is the partial molar Gibbs energy is nothing but partial molar enthalpy of pure minus T into so it's a pure enthalpy of I minus T into pure entropy of I plus RT ln YI. You already know H minus Ts is nothing but G, okay. Again I resubstitute what is Hi minus T into Si, it is nothing but Gi. Okay, that means if you wanted to find out the partial molar Gibbs energy, you should know its pure Gibbs energy plus RT ln YI. Y is the fraction of that particular ith component in the mixture. Okay, this you can use this formula or this formula, any formula you can use to find out the partial molar Gibbs energies. Okay, for example, if it is a binary mixture and G bar A is representing the partial molar Gibbs energy of A, G bar B is representing the partial molar Gibbs energy of B, which is equal to pure Gibbs energy of A plus RT ln YI. RT ln YI representing the mixing of A and B, and this is representing the pure Gibbs energy of A at this temperature and pressure conditions of the mixture. Okay. Similarly, partial molar Gibbs energy of the B is nothing but pure Gibbs energy of B plus RT ln YB. YA and YB are the fractions of A and B in the mixture. So I have rewritten the formulas in this way. for this binary mixture. Either you can use this formula or this formula to find out the partial molar Gibbs energy of A and B in the mixture. So let us evaluate a small simple example so that you can able to connect yourself. Or given example, you have to find out the three things. One is partial molar Gibbs energy of A, partial molar Gibbs energy of B. The third one is total Gibbs energy. Total Gibbs energy in the sense A plus B, okay, which constitute a mixture. Okay, at what conditions you have to find out? Given the temperature equal to 100 degrees centigrade, pressure equal to 3 bar, and fraction of A in the mixture is 0.3 and fraction of B in the mixture is 0.7. Okay, and also given the pure enthalpy of A and pure entropy of A and pure enthalpy of B and pure entropy of B is given. So simply you have to apply this particular formulas to evaluate G bar A and G bar B. Okay, G bar A, okay, at temperature T and pressure 3, which is equal to the pure A enthalpy of A at temperature 100 and pressure 3 minus T, temperature is given 100 degrees centigrade, I have to convert to Kelvin, into S, and pure entropy of A at 103, which is already given here, okay, plus RT ln YI. So I am applying this particular formula. You can see I am applying this particular formula for the case of A and B. So now I substitute everywhere. Example, pure enthalpy of A is given 30, temperature 100 degrees centigrade, pure entropy A is 20, plus R 8.314, T 373 into ln 0.3, which is given a fraction here. Similarly, I got the value of A, and partial molar Gibbs energy of A in the mixture is minus 1168.1, okay, joule per mole. Similarly, similar formula is applied for the case of B. So you get partial molar Gibbs energy of the B at 100 degrees centigrade and T bar is minus 6663.18 joule per mole. What is the third thing I have to find out? What is a total Gibbs energy of the mixture? The total Gibbs energy of the mixture is contributed by the A and B. So I have to summate these two to get the value of the total summation. Okay, I use the summability relationship formula. According to the summability relationship, total Gibbs energy of the mixture can be found out by adding the partial Gibbs energies with respect to its mole fractions. So if I expand the sigma yi G bar I Ig, because I am dealing with the binary mixture here, I can expand that Ya G bar A Ig plus Yb G bar B Ig. G bar A I know, G bar B I know, Ya and Yb I know. So my total Gibbs energy of the mixture constituting A plus B is minus 8014.65 joule per mole. This is how you can able to calculate the partial Gibbs energies of A and B given enthalpy and entropy and mole fraction values. And ultimately what you have found out, see, this is the beauty. Partial Gibbs energy of A and partial Gibbs energy of B nothing but chemical potential of A in the mixture and chemical potential of B in the mixture. Ultimately the chemical potential that is responsible for these separations, purifications, distillations, everything is because of these chemical potentials. Now you have found out whatever the partial Gibbs energy of A is minus 1168.1 is nothing but chemical potential of A in this mixture. Partial Gibbs energy of the B in the mixture is minus 6663.18 is nothing but chemical potential of B in this mixture. That is why any partial molar Gibbs energy is nothing but chemical potential of ith component. Okay, that is why mu Aig chemical potential of A in the ideal gas state is equal to the partial molar Gibbs energy of A in the ideal gas state. Similarly, chemical potential of B in the ideal gas state is nothing but the partial molar Gibbs energy of the B in the ideal gas state. It forms the basis for application of thermodynamics in separation, mixing, distillation, reaction, etc. So this is what we have to get to the conclusion. We have started with the partial molar properties to reach to these conclusions and these formulas. So in summary, what we have learned in the past and 2-3 lectures about the partial molar properties, I have given as a glimpse. You can see partial enthalpy, that means partial molar enthalpy of A in the mixture is H bar I Ig is nothing but pure component. The partial property is nothing but the pure property, because enthalpy does not dependent on the pressure, only depend on the temperature. So whatever the pure property value is nothing but the mixture property. Similarly, what is the partial molar entropy is nothing but pure entropy minus R ln yi. R ln yi comes from the mixing of A and B in the mixture. Similarly, this particular formula just we have discussed right now. Summability relationships. Okay. Ultimately, partial properties and the complete property I want. Complete property is evaluated using summability relationship. Similarly, total enthalpy of the mixture is nothing but sigma yi h bar ig. Total entropy of the mixture is nothing but sigma yi s bar ig. Total Gibbs energy of the mixture is combination of two partial properties, for the binary mixture, sigma yi g bar I ig. So this is what you have found out in a glimpse. You can see there is a mixture, okay, that you have to find out partial property of enthalpy, partial entropy of A, partial Gibbs energy of A. This is partial enthalpy of B, partial entropy of B, and partial Gibbs energy of the B. Okay. Finally, the total enthalpy of A plus B, total entropy of A plus B, total Gibbs energy of the A plus B. This is what these three comes from this summability relationships. I hope now you understood that how we are moving ahead. Okay, and later on we are going to venture into new topics, so please be connected. Thank you.